71% of our planet is covered by water. We've mapped every continent, climbed every mountain, even walked on the moon. Yet more than 80% of Earth's oceans remain unexplored, unmapped, and unobserved by human eyes. Down there in the crushing darkness miles beneath the surface, pressures exceed 8 tons per square inch. Temperatures plunge to just above freezing. No sunlight has penetrated these depths for millions of years. By every measure, it should be a dead zone. Instead, it thrives. Giant squid with eyes the size of dinner plates hunt in eternal night. Fish generate their own light through chemical reactions. Entire ecosystems flourish around volcanic vents that spew superheated, toxic water. Some creatures down there might hold the secrets to immortality itself. The ocean floor is a graveyard of human history, littered with thousands of shipwrecks, lost cities, and crashed aircraft. Strange sounds emanate from the depths that no one can explain. Massive underwater structures appear on sonar that defy geological explanation. We know more about the surface of Mars than we do about our own ocean floor. And what we've discovered so far suggests we've barely scratched the surface of understanding what lies beneath. This is the story of Earth's final frontier, the mysteries that lurk in the deep, and what they might tell us about life, death, and the future of our planet. For most of human history, the ocean was simply a barrier to cross or a source of food. Ancient sailors feared sea monsters and mapped the edges of their world with warnings, "Here be dragons." They weren't entirely wrong to be afraid. The ocean is dangerous, unforgiving, and filled with phenomena that even modern science struggles to explain. The systematic exploration of the deep ocean didn't truly begin until the 20th century. In 1930, William Beebe and Otis Barton descended 1,428 feet below the surface in a steel sphere they called a bathysphere. Peering through a small quartz window, Beebe reported seeing fish that looked like a string of amber lights and creatures that defied all previous descriptions. In 1960, Jack Pickard and Don Walsh piloted the bathyscaphe Trice to the deepest point in Earth's oceans, the Challenger Deep in the Mariana Trench, nearly 7 miles below the surface. The pressure at that depth is over 16,000 pounds per square inch. A human body without protection would be crushed instantly. Yet even there, Pickard and Walsh reported seeing a flatfish swimming along the bottom, proving that life exists even in Earth's most extreme environments. Today, we have sophisticated technology, remotely operated vehicles, autonomous submarines, advanced sonar mapping systems, and pressure-assistant cameras that can withstand the crushing forces of the deep. We've discovered more about the ocean in the past 50 years than in all previous human history combined. But each discovery raises more questions than it answers. Consider this: we've mapped 100% of Mars at a resolution of about 20 feet. We've mapped the moon at similar detail, but we've only mapped about 20% of Earth's ocean floor at that same resolution. The remaining 80% is essentially unknown territory, represented on maps as blank blue spaces or rough approximations based on satellite measurements of the sea surface. Mount Everest, Earth's tallest mountain, rises 29,032 feet above sea level. If you placed Everest at the bottom of the Mariana Trench, its peak would still be more than a mile underwater. The average ocean depth is 12,100 feet, deeper than most mountains are tall. And in these depths, we've found ecosystems that rewrite our understanding of biology, geological formations that challenge our models of how the planet works, and mysteries that remain unsolved despite decades of investigation. Why do massive numbers of sea creatures suddenly beach themselves for no apparent reason? What creates the strange, powerful sounds that hydrophones detect emanating from the deep? How do some sea creatures appear to defy aging and death itself? What lies within the unexplored trenches and underwater caves that cover vast stretches of the ocean floor? Over the next 2 hours, we'll journey into the deep. We'll explore the strange creatures that inhabit the abyss, investigate the geological forces that shape the ocean floor, examine the historical mysteries hidden beneath the waves, and confront the profound questions about life, consciousness, and the future of our planet that the ocean poses. We begin our descent. The ocean is not one environment, but many. Scientists divide it into distinct zones, each with its own characteristics, inhabitants, and mysteries. Understanding these zones is essential to grasping just how alien the deep ocean truly is. The sunlit surface layer, called the epipelagic or sunlight zone, extends to about 650 feet deep. This is the ocean most of us know, warm, bright, full of familiar life like dolphins, sea turtles, and the fish we catch and eat. Photosynthesis occurs here, making this zone the foundation of the ocean's food web. Microscopic phytoplankton converts sunlight into energy, producing half of the oxygen we breathe. But below 650 feet, sunlight begins to fade rapidly. We enter the twilight zone, or mesopelagic layer, which extends down to about 3,300 feet. Here, the light that filters down from above is dim and blue. The pressure increases dramatically, the temperature drops. And the creatures that live here begin to look distinctly otherworldly. In the twilight zone, many fish have developed enormous eyes to capture what little light exists. Others have evolved bioluminescence, the ability to produce their own light through chemical reactions. The hatchetfish has photophores, light-producing organs on its belly that match the faint light filtering from above, making it nearly invisible to predators below. It's biological camouflage at its finest. The lanternfish, one of the most abundant vertebrates on Earth, performs the largest migration on the planet every single night. Billions of these small fish rise from the twilight zone to feed in surface waters after dark, then descend again before dawn. This massive movement of biomass, called diel vertical migration, transfers enormous amounts of carbon from the surface to the deep ocean, playing a crucial role in regulating Earth's climate. Below 3,300 feet, we enter the midnight zone or bathypelagic layer. Sunlight does not reach here. The temperature hovers just above freezing. The pressure is crushing. This zone extends down to about 13,000 feet, and it represents the largest living space on Earth by volume. Yet it remains largely unexplored. Here we find some of the ocean's most bizarre adaptations. The anglerfish, perhaps the most famous deep-sea dweller, has a bioluminescent lure extending from its head like a fishing rod. The light attracts smaller fish, which the anglerfish swallows whole with its enormous, tooth-filled mouth. Female anglerfish can reach several feet in length. Males, bizarrely, are tiny, just a few inches long, and survive by permanently attaching themselves to females, fusing their tissues and sharing blood, essentially becoming parasitic appendages that provide sperm when needed. The vampire squid, despite its ominous name, is actually a gentle creature that feeds on marine snow, dead organic matter that drifts down from above. When threatened, it turns itself inside out, exposing spiny protrusions that deter predators. The gulper eel has a massive mouth that can unhinge to swallow prey larger than itself, essential in an environment where meals are rare and must be seized whenever encountered. Below 13,000 feet lies the abyssal zone, the true deep ocean, extending down to about 20,000 feet. This is a world of perpetual darkness, near-freezing temperatures, and crushing pressures exceeding 600 times atmospheric pressure at sea level. The ocean floor here is called the abyssal plain, a vast, flat landscape covered in fine sediment that has accumulated over millions of years. Life exists even here. Sea cucumbers creep across the seafloor, processing sediment for organic matter. Tripod fish stand on elongated fin rays, waiting for prey to drift by. Giant isopods, looking like enormous pill bugs, scavenge whatever food reaches the bottom. These creatures survive in one of Earth's harshest environments through remarkable adaptations, slow metabolisms, efficient nutrient processing, and the ability to go months without food. But there's one more zone, even deeper, the Hadal Zone, named after Hades, the Greek underworld. This zone begins at 20,000 feet and extends to the deepest points in the ocean, over 36,000 feet in the Mariana Trench. Until recently, scientists believed these trenches might be barren, the pressure simply too great for life to persist. They were spectacularly wrong. In 2014, researchers captured a snailfish living at 26,722 feet in the Mariana Trench. It holds the record for the deepest fish ever observed. The creature is ghostly white, almost gelatinous, with eyes that appear to be degenerating. At these depths, the pressure is so intense that it affects the very proteins that make up cellular structures, yet life persists. Microbes have been found even deeper, in sediment samples from the very bottom of the Challenger Deep. These organisms survive in conditions that seem incompatible with life as we know it. No light, no warmth, crushing pressure, and minimal nutrients. They metabolize so slowly that a single generation might last centuries, yet they are alive, growing, reproducing. Dr. Lisa Levin, a biological oceanographer at Scripps Institution of Oceanography, puts it this way: every time we explore the deep ocean, we find life in places we didn't expect, living in ways we didn't imagine. The deep sea keeps teaching us that life is more resilient, more adaptable, and more diverse than we ever thought possible. But the creatures of the deep don't just challenge our understanding of biology. They force us to reconsider fundamental questions about life itself. If organisms can survive in the crushing darkness of the Hadal Zone, what does that tell us about the possibility of life elsewhere in our solar system? In the ice-covered oceans of Europa, Jupiter's moon. In the methane seas of Titan, Saturn's moon. If life flourishes in Earth's most extreme environments, perhaps we've been too conservative in imagining where else it might exist. And then there's the mystery of bioluminescence itself. Why do so many deep-sea creatures produce light when they live in eternal darkness? The answers are surprisingly complex and reveal sophisticated evolutionary strategies we're only beginning to understand. In the deep ocean, where no sunlight penetrates, up to 90% of creatures produce their own light. This bioluminescence is one of the most widespread adaptations in the marine world, yet it remains one of the least understood. How and why did so many unrelated species evolve this ability? And what are they saying with their lights in the darkness? Bioluminescence in marine animals typically works through a chemical reaction involving a light-emitting molecule called luciferin and an enzyme called luciferase. When these combine in the presence of oxygen, they produce light with remarkable efficiency, converting chemical energy to light with minimal heat production. Some creatures manufacture these chemicals themselves. Others harbor symbiotic bacteria that produce light for them. We've already mentioned counterillumination. Creatures like hatchetfish produce light on their undersides that matches the faint glow from above, erasing their silhouette when viewed from below. But this is just the beginning of how deep-sea animals use light. The flashlight fish has light organs beneath its eyes containing bioluminescent bacteria. The fish can rotate these organs to flash light on and off, using them as searchlights to find food or communicate with others of its kind. The cookie-cutter shark has bioluminescent photophores covering its body except for a dark collar around its neck. From below, the shark looks like a smaller fish, attracting larger predators. When they approach, the shark bites a cookie-shaped plug of flesh from their bodies, a brutal form of parasitism enabled by deceptive lighting. Some squid produce clouds of bioluminescent particles rather than ink when threatened, creating a glowing decoy that distracts predators while the squid escapes into the darkness. It's a smoke screen made of light, a defense mechanism that seems almost magical in its execution. The atoll jellyfish, when attacked, produces a spectacular bioluminescent display called a burglar alarm. Spinning in place, it creates a pinwheel of blue light that pulses outward in waves, the purpose, to attract even larger predators to the scene. The attacker becomes threatened by something bigger and retreats, leaving the jellyfish to drift away. It's calling the police, essentially using light as a distress signal. The anglerfish lure, perhaps the most famous example of bioluminescence, contains symbiotic bacteria that produce light continuously. The bacteria live in a specialized organ filled with blood vessels, receiving nutrients in exchange for their services. The fish can control the intensity and flashing pattern of the light by adjusting blood flow. Different anglerfish species have different lure shapes and lighting patterns, possibly helping them identify potential mates in the darkness. But some of the most spectacular bioluminescence occurs not in fish or squid, but in microscopic organisms called dinoflagellates. When disturbed by movement, these single-celled organisms flash with blue-green light. In large concentrations, they create the phenomenon known as sea sparkle or milky seas, vast stretches of ocean that glow when disturbed by waves, ships, or swimming animals. In 1995, a British merchant vessel reported sailing through a glowing sea covering over 6,000 square miles in the Indian Ocean. The crew described it as like sailing through milk that emitted light. Satellite images later confirmed the event. The glow was likely produced by trillions upon trillions of bioluminescent bacteria responding to some chemical signal. But what triggered such a massive display? Scientists still don't know for certain. Dr. Edith Widder, a marine biologist and bioluminescence expert, has dedicated her career to understanding deep-sea light. She developed the Eye in the Sea, an unobtrusive camera system that uses dim red light, invisible to most deep-sea creatures, to observe them in their natural environment without disturbance. Her recordings revealed complex light-based communications we'd never observed before. Certain squid produce rapid, pulsing light patterns across their bodies that may convey specific messages. Jellyfish coordinate their bioluminescent displays when multiple individuals are present. Some fish produce light in patterns that seem to vary by social context, different flashes for mating versus territorial displays. In 2016, Widder's team captured footage of what appeared to be coordinated bioluminescent signaling among multiple species in the deep sea. Different creatures, unrelated by evolution, seemed to be flashing in synchronized patterns. Were they communicating across species boundaries? Reacting to some common stimulus, or was it simply coincidence? The footage raised more questions than it answered. The study of bioluminescence isn't just about understanding the deep ocean. The same proteins that allow fish to glow are now used in medical research. Green fluorescent protein, originally isolated from jellyfish, has become one of the most important tools in modern biology. Scientists attach it to other proteins to track their movement through living cells, revealing processes we could never observe otherwise. The discoverers of GFP won the Nobel Prize in Chemistry in 2008. Engineers are working on bioluminescent lighting systems for cities that would require no electricity, trees that glow, streets illuminated by genetically modified plants. Others are developing bioluminescent bacteria that could detect toxins or diseases, glowing in response to specific chemicals. The deep-sea creatures that evolved to survive in darkness may ultimately help us develop sustainable technologies for our own world. But perhaps the deepest mystery of bioluminescence is aesthetic. Why do these displays look beautiful to us? The creatures producing them don't have human eyes, don't share our evolutionary history, yet we find their light shows mesmerizing. Is there something fundamental about light, color, and pattern that transcends species? Or are we simply projecting our own sensibilities onto phenomena that have nothing to do with beauty, only survival? The deep ocean communicates through more than light. Sound travels well through water, much better than through air. And the ocean is full of sounds: whale songs, dolphin clicks, fish grunts, and shrimp snaps. But there are other sounds too, strange noises that no one has definitively explained. Sounds that suggest phenomena we don't yet understand. During the Cold War, the United States Navy deployed a vast network of underwater microphones called hydrophones throughout the world's oceans. The Sound Surveillance System, or SOSUS, was designed to detect Soviet submarines. Instead, it revealed an underwater world filled with sounds we'd never imagined existed. Scientists studying the SOSUS recordings discovered that the ocean is anything but silent. Whale songs, already known to researchers, appeared constantly, but so did other sounds: bizarre, powerful, and utterly mysterious noises emanating from the depths. Some were so loud they were detected on sensors thousands of miles apart. Others were so strange they defied easy categorization. In 1997, NOAA hydrophones detected an ultra-low frequency sound rising in frequency over about 1 minute. It was one of the loudest underwater sounds ever recorded, detected by sensors more than 3,000 miles apart. Researchers called it the bloop. The sound's profile was consistent with a living creature, specifically matching the acoustic signature that a very large animal might make. But it was far louder than any known animal's vocalization. Blue whales, the largest creatures ever to exist on Earth, produce sounds that reach about 188 decibels. The bloop was significantly louder. Whatever produced it, if it was biological, would have to be substantially larger than a blue whale. Speculation ran wild. Was there an unknown species of megafauna living in the deep ocean? A relic population of ancient creatures that had somehow survived undetected? The timing of the sound near the Antarctic added to the mystery, with some theorists even invoking H.P. Lovecraft's fictional monster Cthulhu, said to sleep beneath the Pacific. In 2005, NOAA scientists proposed a more mundane but still remarkable explanation: icequakes. As glaciers and ice shelves crack and break, they produce powerful underwater sounds. Analysis suggested the bloop's acoustic signature was consistent with a massive icequake, likely from an Antarctic ice shelf fracturing and carving enormous icebergs. It was almost disappointing, but only almost, because the fact that ice breaking can produce sounds rivaling the loudest creatures on Earth reveals something profound about the forces reshaping our planet as climate change accelerates. But the bloop is just one of many mysterious ocean sounds. Since 1991, hydrophones in the Pacific have detected a sound called upsweep, a continuous, narrowband sound at frequencies between 50 and 70 Hz that rises and falls in pitch over several seconds. It's seasonal, increasing in intensity during certain times of year, and can be detected across much of the Pacific Ocean. No one knows what produces upsweep. The sound doesn't match any known geological or biological source. Some researchers speculate it might be related to volcanic activity on the ocean floor, perhaps resonating through underwater geological structures. Others suggest it could be a previously unknown biological phenomenon, perhaps produced by massive colonies of organisms acting in concert. Nearly 3 decades after its discovery, upsweep remains unexplained. Then there's Julia, detected in March 1999. This sound lasted about 15 seconds and was loud enough to be heard on hydrophones more than 2,000 miles apart. Like the bloop, Julia's audio profile suggested a biological origin, but was far too loud to match any known animal. Further investigation suggested Julia might also be related to iceberg activity, specifically the sound of an iceberg running aground or colliding with the ocean floor. But the debate isn't entirely settled. The sound's characteristics don't perfectly match other documented iceberg sounds, leaving room for alternative explanations. In July 1997, NOAA detected the whistle, a short, rising tone that sounded almost artificial, like a sound effect from science fiction. It was recorded near the location of the bloop, suggesting possible geographic clustering of these phenomena. The whistle remains unexplained. Its unusual acoustic properties don't match typical geological or biological sounds. Some researchers have proposed it might be related to underwater volcanic activity or geothermal vents, but no definitive source has been identified. Another sound, simply called train, consists of long, unvarying tones that reminded researchers of a distant train moving across a landscape. It's been detected in the Pacific since 1997, usually occurring in clusters during certain seasons. Train's characteristics suggest it might be produced by Antarctic ice shelves vibrating or resonating in particular ways, but again, the exact mechanism remains unclear. The sound's regularity and persistence make it one of the more puzzling phenomena in underwater acoustics. Not all mysterious ocean sounds are unidentified phenomena. Some belong to known animals, but raise profound questions nonetheless. Since 1989, hydrophones have tracked a whale whose call is unlike any other. It vocalizes at 52 Hz, a frequency much higher than typical whale songs, which usually range from 10 to 39 Hz. This whale, dubbed the 52 Hz whale or the loneliest whale in the world, appears to migrate along the Pacific coast like other whales, but its calls have never received a response from any other whale. For over 30 years, this creature has been calling out in a frequency no other whale seems to recognize or respond to. *** visual, whale song waveforms, different species ***. Is it a hybrid between two whale species? A deaf whale that learned an abnormal vocalization pattern, a blue whale with an unusual mutation, or simply a whale with a unique voice that others of its kind can hear, but that sounds distinct to human listeners? The 52 Hz whale has never been visually identified, so we don't even know what species it is. It exists only as a voice in the dark, calling across thousands of miles of ocean, apparently forever unanswered. Beyond these specific sounds, the deep ocean is full of ambient noise we're only beginning to understand. Underwater volcanoes grumble and roar, hydrothermal vents hiss and rumble. The Earth's crust itself creaks and shifts as tectonic plates move. Earthquakes produce sounds that travel thousands of miles through the ocean. Even underwater landslides, which can involve cubic miles of sediment, create powerful acoustic signals. Dr. Robert D. Zayek, who leads NOAA Acoustic Monitoring Program, emphasizes that we've barely begun to understand the ocean's soundscape. We've identified and cataloged hundreds of distinct sounds, he explains, but we estimate that represents only a fraction of what's out there. The ocean is speaking, we're just learning to listen. There's a darker side to this story. As we've developed better technology for listening to the ocean, we've also developed technology that makes the ocean much noisier. Military sonar, commercial shipping, underwater construction, seismic surveys for oil and gas. All of these activities produce intense sounds that can travel hundreds of miles through water. Marine mammals, which depend on sound for communication, navigation, and hunting, are increasingly affected by this noise pollution. Mass strandings of whales and dolphins have been linked to military sonar exercises. Some species are changing their vocal patterns, calling at different frequencies or times to avoid human-generated noise. We are essentially shouting in the ocean, drowning out the natural soundscape that marine life has depended on for millions of years. But in the remaining quiet places, in the deep trenches and remote ocean basins far from shipping lanes, the ocean's original voice can still be heard. The songs of whales echoing through the water, the crackle of snapping shrimp colonies, the rumble of the earth itself. a planet that is dynamic, alive, constantly reshaping itself through forces we're only beginning to comprehend. And those forces are more powerful, more violent, and more active than most people realize. The ocean floor isn't a static, unchanging plane. It's a battleground where continents are born and destroyed, where entire ocean basins open and close over millions of years, where volcanic eruptions rival anything seen on land. The floor of the ocean is quite literally the newest surface on Earth. While continental rocks can be billions of years old, oceanic crust is constantly being created and destroyed in a cycle that takes roughly 200 million years. This process, driven by the heat of Earth's interior, shapes not only the ocean basins, but the continents themselves, the climate, and the evolution of life. The longest mountain range on Earth isn't the Himalayas or the Andes. It's the mid-ocean ridge system, a chain of underwater mountains stretching 40,000 miles around the globe like the seam on a baseball. Here, at the ridge crests, new oceanic crust is born. The process works like this. Deep beneath Earth's surface, rock is hot enough to flow like thick syrup. This molten rock, or magma, rises toward the surface where the crust is thin and fractured. At mid-ocean ridges, magma wells up between separating tectonic plates, solidifying into new oceanic crust. The plates move apart at rates of a few inches per year, about as fast as fingernails grow, pulling the ocean basins wider in a process called seafloor spreading. 200 million years ago, the Atlantic Ocean didn't exist. Africa and South America were joined in a supercontinent called Pangaea. Then, a rift opened. Magma welled up. The continents began to separate. Today, the Atlantic grows about an inch wider every year as new crust forms at the mid-Atlantic ridge. In another 200 million years, the Atlantic might close again, the Americas colliding with Europe and Africa to form a new supercontinent. The oceans breathe, expanding and contracting on geological timescales. But if new crust is constantly being created, where does the old crust go? The answer lies at subduction zones, where oceanic plates dive beneath continental plates and sink back into Earth's mantle. These zones are marked by deep ocean trenches, the deepest features on Earth's surface. The Mariana Trench, deepest point in the ocean, is a subduction zone where the Pacific plate slides beneath the Philippine plate. The Challenger Deep, its lowest point, reaches 36,070 feet below sea level. If you dropped a steel ball from the surface there, it would take over an hour to hit bottom. Subduction zones are violent places. As plates grind together, stress builds until it releases catastrophically in earthquakes. The 2011 Tohoku earthquake off Japan, which triggered a devastating tsunami, and the Fukushima nuclear disaster, occurred at a subduction zone. The plate boundary suddenly lurched, lifting the ocean floor by several meters and displacing trillions of gallons of water. The resulting tsunami wave reached heights of over 130 feet in some locations. Most of Earth's major earthquakes and volcanic eruptions occur at plate boundaries, particularly around the Pacific Ocean in a region called the Ring of Fire. This horseshoe-shaped belt is home to 75% of the world's active volcanoes and 90% of its earthquakes. The ocean floor here is a dynamic, dangerous place where the planet's interior forces are at their most violent. But plate tectonics creates more than just earthquakes and volcanoes. In 1977, scientists exploring the Galapagos Rift made one of the most significant discoveries in the history of marine biology: hydrothermal vents, places where superheated water laden with minerals erupts from the seafloor. These vents, called black smokers, when they emit dark, mineral-rich water, can reach temperatures exceeding 750 degrees Fahrenheit. The water doesn't boil despite these extreme temperatures because the pressure at depth is so great. As the superheated water meets cold seawater, dissolved minerals precipitate out, forming chimney-like structures that can grow dozens of feet tall. What shocked researchers was the abundance of life around these vents. giant tube worms, some reaching lengths of 8 feet. Ghostly white crabs and shrimp, clams the size of dinner plates. None of these creatures rely on sunlight for energy. Instead, they are part of an ecosystem based on chemosynthesis. Here's how it works. Bacteria living inside the tube worms' bodies consume hydrogen sulfide and other chemicals from the vent water, converting them into organic compounds through chemical reactions. The worms absorb these compounds for nutrition. They have no digestive system, no mouth, no anus. They are, essentially, mobile housings for bacteria that feed them from within. It's a form of symbiosis, unlike anything seen in sunlight-based ecosystems. The discovery revolutionized our understanding of life's origins. For decades, scientists assumed all life on Earth ultimately depended on the sun. Hydrothermal vents proved this wrong. Life can exist entirely independent of photosynthesis, powered by Earth's internal heat and chemistry alone. Some researchers now believe life itself may have originated at hydrothermal vents. The chemical conditions there, the energy sources, the mineral-rich environment, all could have facilitated the first self-replicating molecules. Life may have been born in darkness, in the crushing depths, long before the first photosynthetic organisms appeared. This has profound implications for astrobiology. Jupiter's moon Europa has a global ocean beneath its ice shell, kept liquid by tidal heating from Jupiter's gravity. That ocean likely has a rocky floor, volcanic activity, and hydrothermal vents. If life can emerge and thrive at Earth's deep-sea vents, it could potentially exist in Europa's ocean too, entirely independent of sunlight. Beyond hydrothermal vents, the ocean floor hosts volcanic activity on a scale that dwarfs anything on land. In 2012, researchers discovered evidence of the largest volcanic eruption in recorded history, not on land, but underwater near the Canary Islands. The Tagoro submarine volcano erupted continuously for months, releasing more than 330 million cubic yards of lava. The event went almost unnoticed by the world because it occurred beneath the waves. When lava erupts underwater, it doesn't flow freely like terrestrial lava. The intense cooling forms distinctive rounded structures called pillow basalts. These pillows stack upon each other, building up volcanic edifices over time. Some underwater volcanoes grow large enough to breach the surface and become islands. The Hawaiian Islands formed this way, built by underwater volcanoes over millions of years as the Pacific Plate slowly moved over a stationary hotspot in Earth's mantle. The ocean floor is also shaped by massive landslides that dwarf anything seen on land. The Storegga slide, which occurred off Norway about 8,000 years ago, involved an estimated 840 cubic miles of sediment, an area roughly the size of Iceland. The resulting tsunami devastated coastlines around the North Atlantic, with waves reaching up to 80 feet high in some locations. These underwater landslides, called turbidity currents when they are flowing, can travel at speeds exceeding 60 miles per hour, carrying enormous volumes of sediment hundreds of miles across the ocean floor. They cut submarine canyons, create massive sediment fans, and reshape the ocean floor on scales we are only beginning to appreciate. Beneath the ocean floor lies another geological mystery with potentially catastrophic implications: methane hydrate deposits. These are ice-like structures where methane gas molecules are trapped within frozen water crystals. They exist in a narrow range of temperature and pressure conditions found in deep ocean sediments and beneath Arctic permafrost. The amount of methane locked in these deposits is staggering, potentially exceeding all other fossil fuel reserves combined. Under the right conditions, this methane could be released rapidly into the atmosphere. Since methane is a potent greenhouse gas, such a release could trigger runaway climate change. Some scientists believe massive methane releases from the ocean floor may have contributed to past extinction events, particularly the Permian-Triassic extinction 252 million years ago, which killed up to 96% of all marine species. Evidence suggests massive volcanic eruptions triggered oceanic warming, which destabilized methane hydrates, releasing enormous amounts of methane into the atmosphere and oceans, causing further warming in a catastrophic feedback loop. Today, we are racing to map and understand the ocean floor before human activities, deep-sea mining, drilling, trawling, fundamentally alter it. The Seabed 2030 project aims to map the entire ocean floor at high resolution by 2030, a task requiring international cooperation and advanced technology. Recent mapping efforts have revealed surprising features: underwater mountains we never knew existed, vast mineral deposits, ancient riverbeds that were above water during ice ages when sea levels were lower. Each new map reveals how little we actually knew about the planet we live on. But the ocean floor holds more than just geological wonders. It's also a vast museum of human history, preserving ships, aircraft, and artifacts that tell the story of our relationship with the sea, a relationship that has often ended in tragedy and mystery. UNESCO estimates there are over 3 million shipwrecks on the ocean floor, spanning thousands of years of human maritime history. Some are famous, their stories known around the world. Others remain mysteries, unidentified hulks that went down for unknown reasons, carrying their secrets to the bottom. The most famous shipwreck in history, the RMS Titanic, wasn't discovered until 1985, 73 years after it sank. The ship lies 12,500 feet down in the North Atlantic, broken in two, slowly being consumed by bacteria that eat the iron hull. Researchers estimate the wreck will be completely dissolved within another few decades, erasing one of history's most tangible links to that tragic night in April 1912. Exploring the Titanic revealed poignant details: shoes lying where bodies once fell, personal belongings scattered across the debris field, the ship's bell still recognizable despite decades of corrosion. But it also revealed something unexpected: an entire ecosystem had grown around the wreck. Fish shelter in the debris, crabs feed on organisms growing on the metal. The Titanic has become an artificial reef, a habitat for deep-sea life. The Titanic is relatively recent. Far older ships lie in the Mediterranean, their wooden hulls preserved by the lack of wood-boring organisms in those depths. Greek and Roman vessels, some over 2,000 years old, rest remarkably intact on the seafloor. Their cargoes, amphorae filled with wine or olive oil, bronze statues, marble columns, tell us about ancient trade networks and economies. In 1900, sponge divers discovered a Roman-era shipwreck off the Greek island of Antikythera. Among the recovered artifacts was a corroded bronze device that would become one of archaeology's greatest mysteries: the Antikythera mechanism. When cleaned and examined, it proved to be an incredibly sophisticated astronomical calculator, using a complex system of bronze gears to predict the positions of celestial bodies. The mechanism's complexity was far beyond anything else known from that era. It wouldn't be until the development of mechanical clocks over 1,000 years later that humans would build anything of comparable sophistication. The device demonstrated that ancient technological achievement was far more advanced than previously believed. How many other such artifacts lie undiscovered on the ocean floor? The ocean floor is littered with treasure ships, vessels carrying gold, silver, and precious gems that sank in storms or battles. The Spanish treasure fleet system, which transported New World wealth to Europe from the 16th to 18th centuries, lost hundreds of ships. Many have been found and salvaged, many more remain lost. The Nuestra Señora de Atocha, a Spanish galleon that sank in a hurricane off Florida in 1622, wasn't found until 1985. The recovered cargo included 47 tons of silver, gold valued at over $400 million in today's money, and priceless artifacts. The discovery sparked legal battles over salvage rights and raised ethical questions about treasure hunting versus archaeological preservation. Not all shipwrecks are ancient or treasure-laden. The ocean floor is also a vast war grave. Over 800 ships were sunk during World War II alone, many with their crews still inside. These wrecks are protected by international law as war graves, yet some have been illegally salvaged for scrap metal, disturbing the final resting places of thousands of sailors. The USS Indianapolis, torpedoed by a Japanese submarine in July 1945, remained lost for 72 years. The ship sank in just 12 minutes, taking 300 men down with it. Of the 900 sailors who initially survived, only 316 would be rescued after days in the water, subjected to dehydration, exposure, and shark attacks. The wreck was finally located in 2017, over 18,000 feet deep in the Philippine Sea. Even in the modern era, ships and submarines disappear under mysterious circumstances. In March 2014, Malaysia Airlines Flight 370 vanished en route from Kuala Lumpur to Beijing with 239 people aboard. Despite being one of the most extensive search operations in history, covering thousands of square miles of the Indian Ocean, the main wreckage has never been found. A few pieces of debris washed ashore in East Africa, confirming the plane crashed, but where it hit the water and why it went off course remain unknown. In November 2017, the Argentine submarine ARA San Juan, with 44 crew aboard, disappeared in the South Atlantic. An explosion was detected near its last known position, but the submarine wasn't found for over a year. When finally located 3,000 feet down, it was imploded, crushed by pressure, offering no clear answers about what caused the disaster. Beyond shipwrecks, the ocean has swallowed entire cities. Rising sea levels since the last ice age, over 10,000 years ago, flooded vast areas of coastline. Archaeological sites that were once on dry land now lie underwater, some remarkably preserved. Pavloptri, off the southern coast of Greece, is believed to be the oldest submerged city known, dating back over 5,000 years. The layout of streets, buildings, and even graves can still be discerned underwater. The site offers unique insights into Bronze Age civilization because it was suddenly abandoned and submerged, essentially frozen in time. Then there's the Yonaguni Monument off the coast of Japan, massive stone structures with apparent steps, terraces, and walls. When discovered in 1987, it sparked intense debate. Is it a natural geological formation or an ancient human-made structure that was submerged when sea levels rose? Most geologists believe the Yonaguni Monument is natural, formed by tectonic activity and erosion. The right-angle cuts and straight edges can be explained by natural jointing in sandstone. But a minority of researchers argue the site shows evidence of human modification, carved symbols, deliberate shaping, intentional architecture. The debate continues. If the monument is artificial, it would date to at least 10,000 years ago, before sea level rise submerged the area. That would make it older than the pyramids of Egypt, older than Stonehenge, from an era we typically associate with hunter-gatherers, not monument builders. If true, it would require rewriting significant portions of human history. Underwater caves hold their own mysteries. The cenotes of Mexico's Yucatan Peninsula are flooded sinkholes that give access to vast underground river systems. Mayan people considered them sacred, throwing offerings into their depths. Modern divers have found human remains, pottery, and gold in these caves, some dating back thousands of years. But some cenote discoveries have been more disturbing. Human skeletons showing signs of ritual sacrifice. Ancient mining operations where people extracted red ochre from cave walls, working in near-total darkness by torchlight. The oldest known underwater mining operations, dating back over 12,000 years, when sea levels were lower and the caves were dry. Cold, oxygen-poor water can preserve human remains remarkably well. In Denmark's peat bogs, which were shallow lakes during certain prehistoric periods, dozens of ancient bodies have been found. The Tollund man, discovered in 1950, died over 2,000 years ago, but his features remain so well preserved that he looks like he died recently. He was likely a ritual sacrifice, hanged and placed in the bog. Similarly, the Clonycavan man from Ireland, dated to over 2,000 years ago, still has hair with a mohawk-like style, apparently fixed with an ancient hair gel made from plant oils and resin. These bodies aren't from the ocean itself, but they demonstrate how underwater environments can preserve the past in ways that dry land cannot. Today, marine archaeologists apply advanced techniques to underwater sites: 3D photogrammetry to map wreck sites, DNA analysis of remains, chemical analysis of artifacts to determine their origins. We are learning to read the ocean floor like a history book, extracting information our ancestors couldn't have imagined. But time is running out for many sites. Climate change is altering ocean chemistry, accelerating corrosion. Treasure hunters loot vulnerable wrecks. Industrial fishing destroys ancient sites with heavy trawling equipment. Each year, irreplaceable pieces of our shared history are lost before they can be properly studied. Yet perhaps the greatest mysteries of the ocean aren't geological or historical, but biological. Creatures that seem to defy the laws of nature. Animals that shouldn't exist, yet do. Life forms so strange that encountering them feels like meeting aliens from another world. Legendary creatures and real monsters. For thousands of years, sailors returned from the sea with tales of monsters, giant serpents that could wrap around ships, enormous squid with tentacles long enough to pluck men from the rigging, mermaids, sea dragons, and creatures without names. Most scientists dismissed these stories as superstition and fantasy. Then we started finding the bodies. The giant squid, Architeuthis dux, was a cryptid, a creature from legend, until 1857, when a partial specimen washed ashore in Denmark. Even then, many refused to believe such creatures existed until more specimens were found. Today, we know giant squid can grow over 40 feet long, with eyes the size of dinner plates, the largest eyes in the animal kingdom. Yet despite being so large, live giant squid evaded scientific observation until 2004, when Japanese researchers captured the first photographs of one in its natural habitat. The first video footage wasn't obtained until 2012. These enormous animals live at depths between 1,000 and 3,000 feet, hunting fish and other squid in the darkness. The colossal squid, Mesonychoteuthis hamiltoni, is even larger. While not as long as giant squid, it's heavier and more massive, with a body built for power rather than speed. Its tentacles are armed not just with suckers, but with sharp hooks that rotate, allowing it to grip prey with devastating efficiency. The largest specimen ever found measured over 30 feet long and weighed nearly 1,000 pounds, and it was likely a subadult. Full-grown colossal squid may be significantly larger. We know colossal squid exist mainly because they are hunted by sperm whales. The whales bear circular scars from squid suckers and hooks, some suggesting squid far larger than any specimen ever captured. Squid beaks found in whale stomachs indicate prey over 40 feet long. The battles between sperm whales and giant squid in the deep ocean must be titanic struggles, though no human has ever witnessed one. Then there's the oarfish, the longest bony fish in the world, capable of reaching lengths over 50 feet. These bizarre creatures have bright red fins, a horse-like face, and a body that undulates through the water like a massive swimming ribbon. They live at depths between 600 and 3,000 feet and are almost never seen alive by humans. When oarfish do appear, it's usually because they've died and washed ashore, often before earthquakes or tsunamis. In Japanese folklore, they are called Ryugu no Tsukai, messengers from the sea god's palace, and their appearance is considered an omen of disaster. Is there any truth to this? Could deep-sea fish detect tectonic activity before earthquakes? Some scientists think it's possible that pressure changes or electric fields generated by stressed rocks might affect deep-sea creatures, driving them to the surface. But the connection remains speculative. The goblin shark looks like something from a nightmare, pink-skinned, with a long, flattened snout and protrusible jaws that shoot forward to grab prey. It's considered a living fossil, virtually unchanged for millions of years. They are rarely seen, living at depths below 330 feet, but specimens have been caught in fishing nets, allowing us to study their bizarre anatomy. The frilled shark is another living fossil, with a body more similar to ancient sharks from 80 million years ago than to modern species. It has an eel-like body and 300 tiny, trident-shaped teeth arranged in 25 rows. When scientists first examined one, they thought they'd discovered a sea serpent. The megamouth shark, despite being over 15 feet long and weighing half a ton, wasn't discovered until 1976. Only a few dozen have ever been observed. It's a filter feeder with a massive mouth filled with tiny teeth, swimming through the water with its mouth open to catch plankton. How did something this large remain unknown for so long? Because it lives at depths of 500 to 3,000 feet and only comes near the surface at night. The Greenland shark might be the world's longest living vertebrate. These massive sharks, growing up to 24 feet long, live in the cold waters of the North Atlantic and Arctic. They are sluggish, moving at less than 2 miles per hour, and feed on fish, seals, and carrion. In 2016, researchers used radiocarbon dating on the eye tissue of Greenland sharks to estimate their ages. The results were stunning. The oldest specimen was approximately 392 years old, give or take 120 years. This shark was likely born around 1620 during the reign of King James I of England. It lived through the entire history of the United States as a nation. These sharks don't reach sexual maturity until they are about 150 years old. But if you want to talk about defying death, consider Turritopsis doanei, commonly called the immortal jellyfish. When injured, sick, or old, this tiny jellyfish can revert to its polyp stage, essentially becoming young again and then grow back into an adult. It can repeat this process indefinitely, making it potentially biologically immortal. The process is called transdifferentiation. Specialized cells transform into different types of cells, allowing the organism to rebuild itself. Similar abilities exist in flatworms and hydra, but the immortal jellyfish is the only known case in a complex animal. Scientists studying this creature hope to understand the mechanisms of aging and possibly develop treatments for age-related diseases in humans. The mantis shrimp possesses perhaps the most sophisticated eyes in the animal kingdom. While humans have 3 types of color receptors, mantis shrimp have 16. They can see ultraviolet and polarized light, perceiving a spectrum of color utterly alien to us. Their eyes move independently and have trinocular vision in each eye, giving them extraordinarily accurate depth perception. But their eyes aren't their only remarkable feature. Mantis shrimp have club-like appendages they use to smash prey with incredible force. The strike is so fast, it accelerates at over 10,000 times the force of gravity that it generates cavitation bubbles. When these bubbles collapse, they produce heat rivaling the surface of the sun for a brief instant and emit a flash of light. The impact hits twice, once from the club itself, then again from the collapsing cavitation bubbles. Few creatures can survive a direct hit. The blobfish, famous for looking like a gelatinous blob of sadness in photographs, actually looks perfectly normal at the depths where it lives, 2,000 to 4,000 feet down. The bizarre appearance comes from rapid decompression when it's brought to the surface. At depth, the pressure keeps its gelatinous body properly formed. At the surface, Without that pressure, it collapses into the droopy, melting appearance that made it an internet sensation. This illustrates an important point. Many creatures we consider bizarre or monstrous look that way because we are seeing them out of their natural context. In the crushing darkness of the deep ocean, adaptations that seem grotesque at the surface make perfect evolutionary sense. Take the barrel-eye fish, which has a transparent skull through which you can see its tubular eyes pointing upward. Those eyes are incredibly sensitive to light, allowing the fish to detect the silhouettes of prey swimming above it against the faint glow from the surface. When it's time to eat, the eyes can rotate forward to see what it's biting. The adaptation is strange but brilliant for its deep-sea environment. The sarcastic fringehead, despite its comical name, is aggressively territorial. When two males encounter each other, they engage in a bizarre ritual, pressing their enormously large mouths together to determine who's bigger. The loser retreats. It's like a very strange kiss that decides dominance without actual combat. Sea cucumbers, those lumpy sausage-shaped creatures on the ocean floor, have a disturbing defense mechanism. When threatened, they can expel their internal organs through their anus, entangling predators in sticky tubules. The organs regenerate later. Some species can even split themselves in two when stressed, with each half regrowing the missing parts. Imagine if humans could sacrifice their digestive system to escape danger, then grow a new one a few weeks later. The vampire squid, already mentioned for its gentle nature despite its name, has skin with numerous light-producing organs that can create dazzling displays. When threatened, it turns itself inside out, exposing bioluminescent photophores and spiny protrusions while keeping its vulnerable parts hidden. It's a defense mechanism that makes the animal look larger and more dangerous than it actually is. Each deep-sea expedition discovers new species: fish with transparent skin, squid that look like string with eyes, jellyfish shaped like alien spacecraft. In 2021, researchers in the Philippines discovered a photosynthetic sea slug that can sever its own head and regrow its entire body from scratch, including heart, digestive system, and all internal organs. The decapitated head crawls around and continues eating while it regrows everything else. Scientists estimate we've discovered only about 10% of marine species. Somewhere between 700,000 and 1 million species remain unknown. Each year, approximately 2,000 new species are described from the oceans. At this rate, it would take centuries to catalog all marine life, and that's assuming no new species evolve and no existing species go extinct in the meantime. But understanding individual species is only part of the puzzle. Some of the ocean's deepest mysteries involve the collective behavior of marine life: massive migrations, unexplained mass die-offs, and synchronized events that span thousands of miles. These phenomena suggest levels of organization and communication in the ocean that we are only beginning to comprehend. Great migrations and mass mysteries every year. Gray whales migrate over 12,000 miles round trip from their feeding grounds in the Arctic to breeding lagoons in Mexico, the longest migration of any mammal. They navigate with precision through open ocean, finding the same locations year after year. How do they do it? We are still not entirely sure. Gray whales don't hold the migration record. That belongs to the Arctic tern, a seabird that flies from Arctic to Antarctic and back each year, a round trip of approximately 50,000 miles. Over its lifetime of 30 years or more, an Arctic tern may fly over 1.5 million miles, equivalent to 3 trips to the moon and back. The European eel has one of the most mysterious life cycles in the animal kingdom. Eels spend most of their lives in European rivers and lakes, but when mature, they undergo a dramatic transformation. Their eyes enlarge, their skin turns silver, their digestive systems atrophy. They stop eating and begin a journey of over 3,000 miles to the Sargasso Sea in the Atlantic Ocean, where they spawn and die. The eggs hatch into transparent larvae called glass eels, which drift on ocean currents back to Europe, a journey that takes 2 to 3 years. When they reach the coast, they transform into elvers, swim up rivers, and begin the cycle again. Despite intensive research, no one has ever observed European eels spawning in the wild. We know where they go, but we've never witnessed the actual reproductive act. Salmon famously return to the exact streams where they were born to spawn, sometimes traveling over 1,000 miles through the open ocean to do so. They navigate using an array of cues: the Earth's magnetic field, the position of the sun, chemical signatures in the water, even visual landmarks remembered from their youth. The precision is remarkable. Studies using genetic analysis have confirmed that salmon from different streams within the same river system maintain distinct populations, rarely interbreeding. Sea turtles show equally impressive navigation. Hatchlings that emerge from eggs buried on beaches immediately crawl to the ocean, where they swim frantically for about 24 hours to reach deeper water. They then spend years, sometimes decades, roaming the open ocean before returning to the exact beach where they hatch to lay their own eggs. Research has shown that sea turtles imprint on the magnetic field of their birth beach. Earth's magnetic field varies subtly from place to place, creating a unique magnetic signature for each location. Turtles can detect these subtle variations and use them as a GPS system to navigate thousands of miles across open ocean. Many marine animals can sense magnetic fields: sharks, rays, lobsters, even some fish. Exactly how they detect magnetism isn't fully understood, but some species have cells containing magnetite, a magnetic ion compound. Disturbances to Earth's magnetic field, like those caused by solar activity, can disrupt animal navigation, possibly explaining some mass strandings. Speaking of strandings, they remain one of oceanography's enduring mysteries. Why do whales and dolphins, sophisticated marine mammals with millions of years of evolutionary adaptation to the ocean, sometimes swim onto beaches where they die? Mass strandings involving dozens or hundreds of animals have been recorded throughout human history. In ancient times, they were considered omens. Today, we understand they are complex phenomena with multiple potential causes, but we still can't predict or prevent them. Military sonar has been implicated in many strandings. High-intensity sonar can cause immediate physical damage to whales' ears and brains. Even non-lethal exposure can panic animals, causing them to surface too quickly, resulting in decompression sickness, the same bends that afflict human divers who ascend too fast. Whales beach themselves not because they are trying to come ashore, but because they are disoriented, sick, or dying. Disease and parasites can also cause strandings. Parasites in the ears and brain can disrupt a whale's echolocation, essentially blinding it acoustically. Viral and bacterial infections can affect balance and orientation. Toxins from harmful algal blooms can poison whales, causing neurological damage. The social nature of many whale and dolphin species can turn a single sick individual's stranding into a mass event. When one animal beaches, its pod mates may follow, unwilling to abandon their companion. This strong social bonding, which serves these species well in the ocean, becomes fatal on land. Some researchers have found correlations between strandings and geomagnetic anomalies, locations where Earth's magnetic field behaves unusually. If whales rely on magnetic navigation, these anomalies might confuse them, sending them off course into dangerous shallow waters. Studies have shown that strandings occur more frequently in areas with unusual magnetic features. Harmful algal blooms, often called red tides, produce neurotoxins that accumulate in the food chain. Fish and shellfish that consume toxic algae aren't killed immediately, but predators that eat them, including whales and dolphins, can be poisoned. The toxins attack the nervous system, causing seizures, disorientation, and paralysis. Several mass strandings have been linked to red tide events. But many strandings remain unexplained. In New Zealand, where mass strandings of pilot whales are particularly common, no single cause accounts for all events. The whales seem healthy, no obvious threats are present. They simply swim onto beaches in large groups and refuse to leave, even when humans attempt to push them back to sea. Whales aren't the only creatures that exhibit mysterious mass behaviors. In recent years, massive squid die-offs have washed thousands of dead Humboldt squid onto beaches from California to Chile. Sometimes the squid are found dead on the surface of the ocean, covering square miles. No definitive explanation has been found, though theories include oxygen depletion, temperature changes, and disease. Jellyfish populations are exploding in many parts of the world, forming vast blooms that can contain billions of individuals. These blooms can devastate fishing industries, clog power plant intake pipes, and even harm swimmers. Some scientists believe warming oceans and overfishing of jellyfish predators are causing the increase. Others think we are simply observing natural cycles we don't fully understand. Perhaps the most spectacular synchronized marine event is coral spawning. On certain nights, determined by moon phase and water temperature, coral colonies across entire reefs simultaneously release eggs and sperm into the water. The timing is so precise that the event occurs within a window of just a few hours on a specific night. The water becomes thick with gametes, looking like an underwater snowstorm. The synchronization is crucial. If individual corals spawned at random times, the eggs and sperm would be too diluted to meet and fertilize. By spawning together, the corals maximize reproductive success. But how do separate coral colonies, sometimes miles apart, coordinate so perfectly they don't communicate directly? Instead, they respond to the same environmental cues: lunar cycle, day length, water temperature. It's an example of emergent synchronization, where simple responses to shared environmental signals create complex coordinated behavior. Similar coordination appears in other species. Certain deep-sea creatures synchronize their bioluminescent flashing when in groups. Crabs migrate in massive coordinated waves. Schools of fish move as one, changing directions simultaneously as if controlled by a single mind. These normal synchronized behaviors make the abnormal ones even more mysterious. When entire populations of a species suddenly die or behave erratically for no apparent reason, it suggests something fundamental in their environment has changed, something we can't easily detect or measure. Climate change is disrupting ancient migration patterns. Fish are arriving at spawning grounds at the wrong times. Birds are finding their traditional feeding areas empty of prey. Whales are changing their routes as ocean temperatures shift. We are witnessing the breakdown of ecological synchronization that took thousands of years to evolve. Which brings us to an uncomfortable truth. The greatest mystery of the modern ocean might be how much damage we are doing to it and how quickly it's happening. The ocean is changing faster than at any time in human history, and we are struggling to understand the full implications of what we've set in motion. The plastic ocean and chemical changes in 1997. Sailor and researcher Charles Moore was returning from a yacht race when he sailed through an area of the North Pacific he'd later describe as a garbage dump in the middle of the ocean. He discovered what would become known as the Great Pacific Garbage Patch, a vast area where ocean currents concentrate floating plastic debris. The garbage patch isn't a solid island of trash, as some media coverage suggested. It's more like a soup, where plastic particles outnumber natural plankton by ratios of 6 to 1 or higher. The patch covers an estimated 1.6 million square kilometers, an area roughly twice the size of Texas. And it's just one of 5 major garbage patches in the world's oceans. Most of the plastic isn't visible from the surface. It's been broken down into tiny particles called microplastics, pieces smaller than 5 millimeters. Sunlight, waves, and chemical processes fragment plastic debris into increasingly smaller pieces. These microplastics are now found in every ocean on Earth, from the surface to the deepest trenches, from polar ice to tropical reefs. Sea turtles eat plastic bags, mistaking them for jellyfish. Seabirds feed plastic pieces to their chicks, filling their stomachs with indigestible material until they starve. Fish consume microplastics that they mistake for plankton. A study in 2015 found that 90% of seabird species have ingested plastic, and by 2050, that number is expected to reach 99%. But the problem goes deeper than mechanical harm. Plastics contain chemical additives, phthalates, flame retardants, stabilizers. When plastic breaks down in the ocean, these chemicals leach out. They're endocrine disruptors, meaning they interfere with hormone systems in animals. They can cause reproductive problems, developmental abnormalities, and immune system dysfunction. Worse, these chemicals bioaccumulate. They build up in increasing concentrations as they move up the food chain. A fish that eats contaminated plankton accumulates chemicals in its tissues. A larger fish that eats many contaminated smaller fish accumulates even more. Predators at the top of the food chain, including humans, receive the highest concentrations. Microplastics have been found in human blood, lungs, and placentas. We are consuming an estimated 5 grams of plastic per week, about the equivalent of a credit card. The long-term health effects are unknown because widespread plastic pollution is such a recent phenomenon. We are conducting an uncontrolled experiment on ourselves and every other form of life on the planet. Over 8 million tons of plastic enter the ocean every year. That's equivalent to dumping one garbage truck full of plastic into the ocean every minute. Since 1950, we've produced over 8 billion tons of plastic, and only 9% has been recycled. The rest persists in the environment, breaking down into smaller and smaller pieces, but never truly disappearing. Particularly deadly are abandoned fishing nets, called ghost gear. These nets, made of durable synthetic materials, can drift through the ocean for decades, continuously trapping and killing fish, sea turtles, dolphins, and whales. An estimated 640,000 tons of fishing gear is lost or abandoned in the oceans each year. Plastic has reached the deepest parts of the ocean. A plastic bag was found in the Mariana Trench, nearly 7 miles down. Every deep-sea expedition now reports plastic debris, bottles, bags, food wrappers in places where no human has ever been. The ocean's remotest depths, once pristine, are now contaminated. But plastic isn't the ocean's only chemical threat. The ocean absorbs about 30% of the carbon dioxide we release into the atmosphere. This might seem helpful for reducing atmospheric CO2, but it's causing a fundamental change in ocean chemistry: acidification. When CO2 dissolves in seawater, it forms carbonic acid. The ocean's pH has already dropped by 0.1 units since pre-industrial times, representing a 30% increase in acidity. That might not sound like much, but ocean chemistry is delicately balanced. Species evolved over millions of years to function within a narrow pH range. Acidification makes it harder for organisms to build shells and skeletons from calcium carbonate. Corals, shellfish, pteropods, tiny swimming snails that are a crucial food source for many fish, all struggle in more acidic water. Coral reefs are particularly vulnerable. They are simultaneously stressed by warming waters, acidification, pollution, and overfishing. We've lost approximately half of the world's coral reefs in the past 30 years. Nutrient pollution from agricultural runoff creates another problem: dead zones. Excess nitrogen and phosphorus from fertilizers causes algal blooms. When the algae die and decompose, bacteria consume oxygen from the water. The result is hypoxic areas where dissolved oxygen levels drop so low that most marine life cannot survive. There are now over 400 identified dead zones globally, covering an area larger than the United Kingdom. Some are seasonal, appearing during certain times of year. Others are permanent. The Baltic Sea has a dead zone the size of Denmark. The Gulf of Mexico's dead zone, fed by runoff from the Mississippi River watershed, can reach over 8,000 square miles during peak periods. Vars, per and polyfluoroalkyl substances, often called forever chemicals, have been found throughout the ocean. These synthetic chemicals, used in everything from non-stick cookware to firefighting foam, don't break down naturally. They accumulate in marine life and have been linked to cancer, thyroid disease, and immune system problems. Even remote ocean water far from any industrial source now contains measurable FARS levels. Mercury contamination from coal-fired power plants and mining operations has made fish consumption a health risk. Mercury bioaccumulates particularly efficiently, reaching dangerous concentrations in large predatory fish like tuna, swordfish, and shark. Pregnant women are advised to limit consumption of certain fish species because mercury can damage fetal brain development. Pharmaceutical drugs excreted by humans and livestock find their way to the ocean through sewage systems and agricultural runoff. Antidepressants, antibiotics, hormones from birth control pills all have been detected in marine organisms. Fish exposed to these chemicals show altered behavior and reproduction. We are literally drugging the ocean without understanding the consequences. Even sunscreen is a problem. Chemicals like oxybenzone and octinoxate, found in many sunscreens, cause coral bleaching and DNA damage. Hawaii and other jurisdictions have banned certain sunscreen formulations to protect reefs. It's a small example of how even well-intentioned human activities can harm marine ecosystems. Chemical pollution gets most attention, but noise pollution is equally serious. The ocean has become dramatically noisier over the past century. Commercial shipping produces constant low-frequency noise that can travel hundreds of miles. Seismic surveys for oil and gas exploration use air guns that produce sounds exceeding 250 decibels. Naval sonar can be heard across entire ocean basins. Marine mammals depend on sound for everything: communication, navigation, finding mates, hunting prey. Excessive noise interferes with all these activities. Whales must shout over background noise to be heard. They change their calling frequencies, migration routes, and feeding behaviors to avoid noise. Some simply abandon areas they've used for generations. Even light pollution affects the ocean. Coastal lighting confuses sea turtle hatchlings, causing them to crawl toward cities instead of toward the ocean. Artificial lights attract and disorient seabirds. Fish behavior and migration patterns are altered by lights on boats and offshore platforms. Climate change amplifies all these problems. Warmer waters hold less oxygen, expanding dead zones. Stronger storms stir up plastic debris and pollutants from sediments. Changing ocean currents alter how pollutants spread. Species stressed by warming are more vulnerable to chemical toxins. We're approaching potential tipping points, thresholds beyond which the ocean cannot recover without centuries of intervention. The collapse of major fisheries, the loss of coral reef ecosystems, the disruption of ocean currents that regulate global climate. These aren't hypothetical future scenarios. They are happening now, unfolding in real time. And we're about to make things worse. The next frontier of resource exploitation is the deep ocean floor itself, home to valuable mineral deposits. Deep-sea mining, once science fiction, is becoming reality, and it may be the greatest threat the ocean has ever faced. Deep-sea mining and the future of the ocean, scattered across vast stretches of the deep ocean floor, lie potato-sized rocks called polymetallic nodules. They contain manganese, nickel, copper, cobalt, and rare earth elements, minerals essential for batteries, electronics, and green technologies. As demand for these materials increases, mining companies are preparing to harvest them from the seafloor. The proposed mining technique involves deploying massive machines to the ocean floor, several miles down. These machines would crawl across the seafloor like underwater combine harvesters, scooping up nodules and pumping them to surface ships through long pipes. Behind them, they'd leave barren swaths of disturbed sediment. The environmental consequences are difficult to predict, but almost certainly catastrophic. Mining machines would destroy every organism in their path, creating dead zones in areas that took millions of years to develop. The sediment plumes generated by mining would spread for hundreds of miles, smothering life far beyond the immediate mining area. Noise and vibration would affect animals across vast regions. Deep-sea ecosystems are incredibly fragile. Organisms grow slowly, reproduce infrequently, and recover from disturbance over timescales of decades or centuries. A single pass of a mining machine could eliminate species we haven't even discovered yet. Scientists estimate that many deep-sea species exist only in small, localized areas. Mining could drive them to extinction before we know they exist. In 1989, a small-scale mining test in the Pacific left tracks visible on the seafloor 26 years later. The ecosystem had not recovered. Where mining occurred, diversity remained dramatically lower than surrounding areas. If this is the impact of a single small test, imagine the effects of industrial-scale operations covering thousands of square miles. Some companies are targeting hydrothermal vents, which contain concentrated deposits of valuable minerals. These ecosystems are among the most unique on Earth, home to species found nowhere else, living in conditions that may replicate how life first emerged. Mining them would be like destroying the Galapagos Islands for their resources while we are still discovering what lives there. Who owns the deep ocean floor? The question is legally complex. Beyond nations' territorial waters, the ocean floor is considered the common heritage of mankind under international law, administered by the International Seabed Authority. This body is tasked with both allowing exploitation of marine resources and protecting the marine environment, potentially conflicting mandates. Mining companies and their supporters argue that deep-sea minerals are necessary for the transition to renewable energy. Electric vehicle batteries require cobalt, nickel, and manganese. Wind turbines need rare earth elements. If we are serious about addressing climate change, they argue, we must access these resources wherever they exist. Environmental organizations counter that terrestrial mining is already supplying these materials, and that increased recycling, material substitution, and reduced consumption could meet future demand without touching the deep ocean. They point out that we don't fully understand deep-sea ecosystems and cannot possibly predict all consequences of industrial-scale mining. Here's a sobering fact. We've explored less than 1% of the deep ocean floor. We are contemplating industrial exploitation of environments we barely understand. It would be like clear-cutting a rainforest before we'd studied 99% of its species, geography, or ecological functions. The deep ocean may hold resources far more valuable than minerals. Marine organisms produce unique chemical compounds that could yield new medicines. Already, compounds from sea sponges have led to anti-cancer drugs. Chemicals from cone snails provide powerful painkillers. Enzymes from deep-sea bacteria are used in COVID-19 tests. What other medical breakthroughs might exist in species we haven't discovered? Some companies are bioprospecting, sampling marine organisms for genetic and chemical resources. This raises questions about ownership and benefit sharing. If a company discovers a valuable compound in a deep-sea creature, who benefits? The company, the international community. The developing nations, whose nearby waters were sampled. The deep ocean is also a military frontier. Submarines operate in deep water. Undersea cables carry most of the world's internet traffic. Surveillance systems monitor for submarine activity. Nations are developing underwater drones, autonomous weapon systems, and secret installations on the ocean floor. The deep sea is becoming militarized, raising questions about security, environmental protection during military activities, and the risk of conflict. Some scientists have proposed geoengineering schemes involving the ocean, fertilizing vast areas with iron to stimulate phytoplankton growth and increase CO2 absorption, pumping CO2 directly into deep ocean water for storage, even modifying ocean chemistry to counter acidification. These proposals are controversial. They could help address climate change, or they could trigger unforeseen ecological cascades that make things worse. Small-scale iron fertilization experiments have shown mixed results. Sometimes they stimulated phytoplankton blooms as expected. Other times they had no effect or triggered blooms of toxic algae. The ocean is too complex for simple engineering solutions. Interventions that seem straightforward on paper become unpredictable in practice. Some human activities offer hope. Sustainable fishing practices, where catch limits are based on scientific assessment and enforcement is effective, have allowed depleted fish stocks to recover. Marine protected areas, where fishing and development are restricted, have proven effective at preserving biodiversity and helping damaged ecosystems heal. Scientists are developing techniques to restore damaged coral reefs, growing coral in nurseries and transplanting it to degraded reefs, using electricity to stimulate coral growth on metal structures, breeding heat-resistant coral varieties that might survive warming waters. These efforts show promise, though they are small in scale compared to the damage occurring globally. Organizations are developing technologies to remove plastic from the ocean, floating barriers that concentrate surface plastic for collection, filters that remove microplastics from water, even bacteria engineered to break down plastic. Some projects have shown initial success, though critics argue prevention is more important than cleanup. The ocean itself offers clean energy. Offshore wind farms, wave energy converters, tidal power generators, ocean thermal energy conversion systems that exploit temperature differences between surface and deep water. These technologies could provide massive amounts of renewable energy while having relatively low environmental impact if properly designed and sited. Deliberately sunk ships have become artificial reefs, providing habitat for marine life. Old oil platforms, when decommissioned, sometimes become valuable fish habitat, so much so that in some cases it's preferable to leave them in place rather than remove them. We can build habitat as well as destroy it. Coastal ecosystem restoration, replanting mangroves, restoring salt marshes, protecting seagrass beds, provides multiple benefits. These ecosystems absorb CO2, protect shorelines from storms, filter pollutants, and provide nursery habitat for commercially important fish. They are relatively inexpensive to restore and maintain, offering high returns on investment. In 2023, after years of negotiation, nations reached an agreement on the High Seas Treaty, establishing a framework for protecting biodiversity in international waters. It's a step toward comprehensive ocean governance, though implementation and enforcement remain challenges. Individual actions matter too. Reducing plastic consumption, choosing sustainable seafood, supporting effective ocean conservation organizations, advocating for strong environmental policies. These collective actions shape how humanity treats the ocean. Young people, particularly those who will live with the consequences of today's decisions, are increasingly vocal about ocean protection. Youth climate activists are expanding their focus to include ocean health. They understand intuitively what science demonstrates. The ocean and climate are inseparably linked, and we cannot solve one problem without addressing the other. Which brings us to perhaps the most important ocean mystery of all. How will the ocean respond to rapid climate change? The ocean has always regulated Earth's climate, but we are altering it so quickly that its ability to maintain stability may be compromised. The consequences could reshape not just the ocean, but all life on Earth. The ocean's role in climate and what's changing the ocean is Earth's climate control system. It distributes heat around the planet through massive currents that move water in predictable patterns. Without these currents, the temperature difference between equator and poles would be far more extreme, rendering much of Earth uninhabitable. The Gulf Stream carries warm water from the tropics northward along the US, East Coast, and across the Atlantic to Europe. This current is why London has milder winters than cities at similar latitudes in Canada. The Gulf Stream is part of a larger circulation pattern called the Atlantic Meridional Overturning Circulation, or AMOC. Here's how AMOC works. Warm surface water flows north. As it reaches the Arctic, it cools and becomes saltier through evaporation and ice formation. Cold, salty water is dense, so it sinks, flowing back south as a deep current. This conveyor belt-like circulation moves enormous amounts of heat and salt around the Atlantic. AMOC is weakening. Since the mid-20th century, it has slowed by about 15%. The reason? Melting Arctic ice and increased precipitation are adding fresh water to the North Atlantic, making surface water less dense and less likely to sink. If AMOC weakens substantially or collapses, climate patterns throughout the Northern Hemisphere could change dramatically. If AMOC collapsed, Europe could cool significantly even as the rest of the world warms. Tropical rain patterns would shift. Sea levels along the US East Coast could rise by an additional foot or more. Fish stocks would relocate. The consequences would cascade through ecosystems and human societies. This has happened before. About 12,000 years ago, AMOC rapidly weakened during a period called the Younger Dryas. Temperatures in Europe plummeted. The event lasted about 1,000 years before AMOC resumed and temperatures recovered. The trigger was likely freshwater from melting North American glaciers flooding into the North Atlantic. The ocean absorbs over 90% of the excess heat trapped by greenhouse gases. This has buffered atmospheric warming, preventing even more severe temperature increases on land. But it comes at a cost. Marine heat waves are becoming more frequent and intense. In 2016, a marine heat wave in the Coral Sea reached temperatures several degrees above normal for months. The Great Barrier Reef experienced the worst bleaching event in its history, with 29% of corals dying. In 2020, another heat wave caused further widespread bleaching. The reef is fundamentally altered, with fast-growing but less structurally complex corals replacing slow-growing species. Marine heat waves have devastated kelp forests off California, Australia, and elsewhere. When water warms beyond kelp's tolerance, the plants weaken and die. Sea urchins, whose predators have often been overfished, consume the remaining kelp faster than it can regrow, creating urchin barrens, areas where once thriving forests are replaced by bare rock covered in spiny urchins. Fish are moving poleward to stay within their preferred temperature ranges. Commercial fishing grounds are shifting. Species that never previously coexisted are now interacting, with unpredictable consequences. Tropical fish are appearing in temperate waters. Arctic species are running out of habitat as their cold water refuges shrink. Warming is also increasing ocean stratification, the tendency of water to form distinct layers that don't mix well. Warm water is less dense than cold water, so as the surface warms, it becomes more buoyant and less likely to sink and mix with deeper water. This reduces the flow of nutrients from deep water to the surface, potentially limiting the productivity of ocean ecosystems. Warmer water holds less dissolved oxygen than cold water. As the ocean warms, oxygen levels are declining, and oxygen minimum zones, regions where dissolved oxygen is naturally very low, are expanding. Some areas are becoming inhospitable to most marine life, forcing animals to relocate or adapt rapidly. Sea level is rising at an accelerating rate. The current rate is about 3.3 millimeters per year, more than twice the rate observed in the 20th century. The rise comes from two sources: thermal expansion as water warms and physical expansion as glaciers and ice sheets melt and add water to the oceans. The Greenland and Antarctic ice sheets contain enough frozen water to raise global sea levels by over 200 feet if they melted completely. While complete melting would take centuries, even partial melting poses serious threats. Current projections suggest sea level could rise by 1 to 2 meters by 2100, but recent observations of accelerating ice loss suggest it could be higher. Over 600 million people live in coastal areas less than 10 meters above sea level. Cities like Miami, New York, Shanghai, Mumbai, and Bangkok face increasing flood risks. Small island nations like the Maldives and Kiribati could become largely uninhabitable. Climate refugees from sea level rise could number in the tens of millions within this century. Rising seas amplify storm surge, the wall of water that hurricanes push ashore. A hurricane that once would have caused manageable flooding now causes devastating inundation. Warmer ocean water also fuels stronger hurricanes. We are seeing storms intensify rapidly, giving less warning time and maintain strength longer after making landfall. Perhaps most concerning is the potential for feedback loops, changes that accelerate further warming. As Arctic permafrost thaws, it releases methane and CO2 trapped for thousands of years. This adds greenhouse gases to the atmosphere, causing more warming, thawing more permafrost. Similarly, as Arctic sea ice melts, dark ocean water absorbs more sunlight than reflective ice did, causing further warming. We discussed methane hydrates earlier. As ocean bottom water warms, particularly on continental slopes and in the Arctic, these hydrates could destabilize, releasing massive amounts of methane. The potential scale of release and its timing are highly uncertain, but the risk is real. Climate scientists have identified several potential tipping points, thresholds beyond which changes become self-sustaining and difficult or impossible to reverse. Amok collapse is one, large-scale permafrost thaw is another. Amazon rainforest dieback, Antarctic ice sheet collapse, coral reef extinction, each could trigger cascading effects that fundamentally alter Earth's climate system. The geological record shows that Earth's climate has been both warmer and colder than today. During the Eocene, about 50 million years ago, the planet was ice-free and crocodiles lived near the poles. During ice ages, massive glaciers covered much of North America and Europe. What makes current changes alarming isn't just the magnitude, but the speed. Past climate changes typically occurred over thousands of years, giving species time to adapt or migrate. We are causing similar magnitude changes in decades. Most species cannot evolve fast enough to keep pace. The result is extinction, rates approaching those of past mass extinctions. The ocean's ability to absorb CO2 may be diminishing. As surface waters become more saturated with CO2, their capacity to absorb more decreases. If ocean circulation slows, less CO2-rich surface water gets mixed into the deep ocean where it would be stored for centuries. The ocean has buffered our emissions, but that buffer is not infinite. Some scientists propose radical interventions, reflecting sunlight back to space with artificial particles in the upper atmosphere, seeding clouds over the ocean to increase reflectivity, even installing mirrors in space. These schemes might work, but they carry enormous risks. Unintended consequences could be catastrophic, and once started, some interventions would need to continue indefinitely. Natural solutions offer safer approaches, protecting and restoring blue carbon ecosystems like mangroves, salt marshes, and seagrass beds that sequester carbon in sediments, ending overfishing so marine ecosystems can function properly, protecting biodiversity so ecosystems remain resilient, reducing pollution so the ocean can better handle climate stress. Ultimately, addressing ocean and climate changes requires dramatically reducing greenhouse gas emissions. This means transitioning from fossil fuels to renewable energy, improving energy efficiency, changing agricultural practices, protecting forests, and fundamentally rethinking our economic relationship with the natural world. The Paris Agreement commits nations to limiting global warming to well below 2 degrees Celsius above pre-industrial levels. We are not on track to meet that goal. Current policies put us on pace for about 3 degrees of warming by 2100, with catastrophic consequences for ocean ecosystems and the billions of people who depend on them. The changes are not distant future problems. They are happening now. Fishermen are seeing species disappear from traditional fishing grounds. Coastal communities are experiencing more frequent flooding. Indigenous peoples in the Arctic are watching their cultures, built around sea ice, become impossible to maintain as ice vanishes, but there is still time to act. Every fraction of a degree of warming we prevent, every marine ecosystem we protect, every policy change we implement makes a difference. The ocean has remarkable resilience if we give it a chance to recover. So we return to where we started, to mysteries, but not the mysteries we expected. The deepest mystery isn't what lives in the ocean, or how it formed, or even where it's going. The deepest mystery is whether we, as a species, have the wisdom to recognize our dependence on the ocean and the will to protect it before it's too late. Conclusion. We began this journey in darkness, descending through the ocean's layers into the abyss. We've encountered creatures that defy imagination, geological forces that shape continents, ecosystems powered by chemistry instead of sunlight. We've explored shipwrecks that tell human stories and migrations that span hemispheres. We've confronted uncomfortable truths about how we are changing the ocean, often in ways we don't fully understand. The ocean remains mysterious, not because we lack technology to explore it, but because it's fundamentally more complex than we imagined. Each answer reveals new questions. Every expedition discovers species we never knew existed. We're like children who have waded ankle-deep into a vast sea and declared we understand oceans. But our ignorance hasn't prevented us from profoundly altering marine ecosystems. We've removed 90% of large fish. We've filled the ocean with plastic that will persist for centuries. We've changed the ocean's chemistry through carbon emissions, warmed it through greenhouse gases, made it noisier, brighter, and more polluted. We've done all this while still exploring less than 1% of the deep ocean floor. Yet there is hope. More people understand the ocean's importance than ever before. Scientists are working to map the ocean floor, catalog marine species, and understand ocean processes. Engineers are developing technologies to clean pollution and reduce our impact. Policymakers are creating marine protected areas and international agreements. Citizens are demanding action. The next generation understands what's at stake. They know the ocean produces half the oxygen they breathe. They know it regulates climate, provides food for billions, and supports Earth's biosphere. They know that humanity's fate is linked to the ocean's health, and they are demanding we act accordingly. The ocean has survived 5 mass extinctions, asteroid impacts, ice ages, and volcanic eruptions that turned day into endless night. It has remarkable resilience. If we reduce pressures, protect critical habitats, allow depleted populations to recover, the ocean can heal. We've seen it happen: marine reserves where fish populations rebound, restored reefs where corals grow again, areas where cleanup efforts make a visible difference. From space, Earth is a blue planet. Not green, not brown, but blue. Water covers most of its surface. The ocean connects all continents, all nations, all peoples. What happens in one ocean basin affects the others. We truly are one planet, one ocean, one interconnected system. The ocean keeps its mysteries. We don't know what lives in the deepest trenches. We can't predict exactly how climate change will alter marine ecosystems. We haven't discovered most of the species that exist in the deep, and perhaps that's as it should be. Some mysteries invite exploration, some remind us of our limits, some inspire wonder. But the mystery we must solve isn't scientific, it's ethical. How do we live on a blue planet without destroying what makes it livable? How do we take